the Unit 7 test was last week. If you want to do corrections to that test for up to 10 points back, remember you can still do that. It opened, it was not open Friday. I know I had some people ask, but I had people making up the test Friday that had missed it on Thursday. So, but it is open now if you would like to do test corrections to the Unit 7 test. And then if test corrections, 10 points, does not bring you to passing, if you kind of bombed that test, you can then choose to do a retest. Okay, a retest is for up to a 70. So if you would like to retest, you do need to sign up to come to CatTrax. You can't retest outside of class. You can do corrections outside of class, but not a retest. Unit 6, that Unit 6 test from way back when, it's been a few weeks now. I've only had one person retake this test, and just a handful have done test corrections. Okay, you can still correct the Unit 6 test and get that test grade up to 10 points, or retake it for up to a 70 if needed. Okay, so those are the biggest effects on your grade, are test grades. So those of you who need to get your average up, start with the test. The review for both of those, okay, the review for Unit 6 and the review for Unit 7 in AWARE are both still open. Those of you who have not submitted, you have a 0 for the review. You can still submit those for credit. I'll still take them. If you submitted the review just to get it submitted and you did poorly and you want me to reopen it so you can try to correct the ones you missed, all you have to do is ask. I'll reopen the review for you and you can rework the ones you missed. Make note, look at your results, make note of which ones you need to go back and try again on. Okay, and then you can resubmit and let me know and I'll update that grade. And then of course, Delta Maths. Delta Maths are still open for late credit. Let me get a Delta Math window open here to do a sample student page. You have a lot of possible assignments that will show up under the past due tab, late credit available. It's everything since we came back in January. Okay, so all of this from Unit 6 and Unit 7, you can see everything's at 50% credit now. Because remember, if you do it late, it's at 75% credit till the test, and then it drops to 50. So you may be like 80% done with an assignment, but it still shows up here because you've got that 20% to finish. You can finish that 20% and get half credit on that 20%. You still get the full credit for what you did on time. But if anything is showing up here, if you see any of these assignments under past due, you can go get those grades up. Okay, and then this one was due last night, or actually, I have to look back on our calendar. It was assigned on the 11th. So that one was due on the 13th. Okay, so I was giving you a full, a couple of school days late to get it done. So even though that is from the last unit, it's still at 75% credit through tomorrow. So that one you can still get 75% credit on, and then it's going to drop to 50. Okay. So any questions about what you could possibly still do to get your grade up? Let me know. Sign up for my CatTrax. Seniors, I think you have a senior meeting today, so I don't think any of y'all have a tutorial today in CatTrax. I think you're assigned to the senior meeting, but you've got a couple days of CatTrax tomorrow and Friday, and then on Friday you can sign up to come to me next week for corrections or retakes as needed. Okay, one thing I did want to point out about CatTrax that's upcoming is that in the library, they're going to be hosting, here it is, a Adulting 101 series, okay, during CatTrax next week, and then the week before spring break, I believe it is. So these are the dates, the 2 Fridays that you can start signing up for these during CatTrax in the library. Okay, so here's the schedule. So there's 4 next week. Okay, so you can sign up this Friday in RTI Scheduler. You can search for these on these days in cat tracks, and they're going to be in the library. Okay, so strategic financial plan, investing 101, preparing to lease or own a home, and how to become a realtor if you're interested in that. Okay, so there's different people coming in to speak on these topics and hopefully help you learn some things that you may need once you graduate. Okay, so that's next week. So you can sign up Friday. And then the week before spring break, there's 3 options here: career opportunities in maritime. Okay, we have a lot of that near us. Okay, we're close to the bays, to the Gulf. Okay, so lots of maritime job opportunities you may never have heard of. Okay, so there'll be a speaker talking about those. There's estate planning, so talking about a will and DNRs and some documents, legal documents that you may want to consider how to go about getting those filed and planned. And then if you're interested in construction and building apprenticeships, paid apprenticeships, so if you want to get into that field, there will be a speaker on Thursday the 13th. Okay, so just some opportunities for y'all, especially as seniors, in some upcoming cat tracks. All right, so now let's get going with Unit 8. Okay, so Unit 8 is all about exponential functions. Today we're focusing on graphing. Okay, we're going to look at the parent functions graph, and then we're going to use Desmos to help us graph some examples. As we look at the parent function, I'm going to just talk about some of the key attributes and features that you should really be able to recognize that are going to help you graph other transformed exponentials. So the parent function looks like this. You have a times b to the power of x. Okay, x is in the exponent. That's what makes a function exponential, is that the x is in the exponent. Okay, so that right there, x is in the exponent, that's exponential. Then the a and the b value are letters because they're variable. They can change. So a, we should recognize. Every function we've talked about, we have had a coefficient of a in front of it. Okay, that a is multiplied by the function, which could reflect the graph if it was negative, right? Or it could vertically stretch or compress the graph if it's something other than 1. Okay, in the parent function, that a value is an understood 1. Okay, now the b, that's new. We haven't had a b in our functions before. That is new for exponential because the exponent x has to be on some base value. Okay, so that b is the base. If you want to make note of that somewhere, you can call b the base. Now the base value is going to be something other than 1. It has to be something other than 1, because if it's a 1, what is 1 to any power? If I square 1, cube 1, quadruple, whatever, it's always going to be 1, because 1 times 1 times 1, however many times, is still 1. So b cannot be 1. If you want to make note of that, b cannot be 1. Okay, so it's got to be something other than 1. So there's 2 possibilities. That b can be greater than 1. Okay, so a 2, for instance, is a common base that you will see. Okay, or that b could be a fractional value. Here it's saying it's between 0 and 1. Okay, so like 1/2, for example. Okay, what differences do you notice in these 2 graphs with a b that's greater than 1 versus less than 1? Do those graphs look the same, or is there something different about them? What's different? So if I were to trace this first graph, how would you describe what I'm doing? Okay, the slope or the change is, say it again. They're going different directions. This one's going up. Remember, we call that increasing. So we read a graph from left to right. This graph is increasing. And what's this graph doing? decreasing. So the B value is going to determine whether your exponential is increasing or decreasing. They're both a similar shape, okay? It is increasing exponentially, which means as you keep going, see the rate of change between the 2 points? Horizontally, all these points are 1 unit apart, okay? But vertically, these are really close. And then those are a little further, and then a little further, and then further, and they keep getting further and further apart vertically. That's exponential growth. Okay, when it's increasing, it's growth. Okay, this is decreasing exponentially. It means these points, as we move to the right, these points are getting closer and closer and closer together vertically. Right? Do y'all see that? This is called, the word for that is decay. So we've got growth and decay. Exponential growth, exponential decay. Okay, that's when we're increasing versus decreasing. Okay, so I'm going to make just some notes of that vocabulary here off to the side. Okay, so this is increasing. Now, remember when we talk about increasing and decreasing intervals, we say we're reading the graph from left to right. So that's X values. Okay, the X-axis goes left to right. So we give intervals where it's increasing or decreasing. These graphs don't have the arrows drawn. You can add in the arrows so that it's more clear. They just go to the edge. When a graph goes to the edge like this of the grid, okay, there's not a point drawn. That means it's assumed to continue. Okay, these graphs go on forever. So this graph is increasing from negative infinity on the left to positive infinity on the right. This graph is decreasing from negative infinity on the left to positive infinity on the right. Okay, and I told you that this is called exponential growth. And this one is called exponential decay. Okay, if something is decaying, it's going away, right? It's decreasing. Okay, if it's growth, it's going up, it's increasing. All right, so the reason, okay, that one is increasing and decreasing, it's all about that B value. Okay, so that B value is what tells us that it's increasing, okay, or decreasing. So B value is going to determine that for us. Now, some people are asking, okay, in my previous class or in previous years, I've had this question. So I just want to go ahead and address it. Why does the change in those are both positive values, so why is one decreasing if it's still a positive number? Okay, it's because it's the base of an exponential. We have to remember exponent rules. Okay, so exponent rules that help us to graph exponential functions, one of them is anything raised to the 0 power is what? Who remembers this rule? I'm just going to put it up here at the top. Anything, we'll say B since we're using B to the base. Anything to the 0 power is what? Does anybody remember that exponent rule? If you were to type this in Desmos, you could do 2 to the 0 power, or 1/2 to the 0 power, or 1,000,000 to the 0 power. Anything to the 0 power is always going to come out as 1. So what you'll notice in both of these, okay, whether it was a greater than 1 B value or a less than 1 B value, look at the table of values. When X is 0, what is Y? For both of them. That's our y-intercept here. You can see on the graph, whether it's increasing or decreasing, both of them cross the y-axis at 1. Because it doesn't matter what the base is, anything to the 0 power is 1. Okay, so they do both have the same y-intercept. Okay, so I'm going to put that up here in the general parent function. I'm going to just make note that the y-intercept is going to be at 0, 1. Okay, The base does not affect that. Now, if there's transformations that happen, bless you, transformations that happen, yeah, the graph can shift around and that will move. But if it's just the base that's changing, the y-intercept's not going to change. Okay. Now, another exponent rule that I'm going to jot down up here that you may or may not remember is when you raise a base, it doesn't matter what the base is, I'll call it b again, to a negative power. Let's say I raise it to the -2. If you have a negative exponent, remember to get rid of that negative in your exponent, you have to move the term that's raised to the power, in this case b, within the fraction. So that b has to come down and come to the denominator, and now it can be to the +2 power. Now, there's nothing in front of this b right now. Let's say there was some a value, though, in front, because it's a times b to the x. That a value doesn't move. That a value is not part of what's being raised to the power. So the a would stay up there in the numerator. Just the value that's being raised to the negative power moves. So for instance, if I have, let's say 2 to the -1 power, it's going to move the 2 to the denominator, and that 1 can now become a positive. Now, is there an a value in front of this 2? Is there anything multiplied in front? So what is understood to be my a value if it's not written? A 1. So it would just be a 1 in the numerator. So that would just be 1/2. So 2 to the -1 power is 1/2. Okay, or if you were to do that with a fraction, if we had 1/2 to the -1 power. When we raise a fraction to a power, we need to recall that both the numerator and the denominator get that power. So the 1 is to the -1 power, and the 2 is to the -1 power. So both of those have to move within the fraction to get rid of those negative powers. So the 2 has to move to the numerator, and the 1 has to move to the denominator. And they both become a +1 power on those, which that's just 2 over 1, which is just 2. Okay, so this is just refreshing on that negative exponent rule. This negative exponent rule, okay, will change what our fractions do or what our values do as we go left of that y-intercept. So we've identified where the y-intercept should be, but if we have a base value greater than 1, okay, and we raise it to powers, see these on the table where x is negative, the values get smaller. So as we move to the left, the values get smaller and smaller and smaller because they're changing to fractions. Okay, and it's going to be smaller and smaller and smaller fractions, getting closer and closer and closer to 0, right? If this was a 3 to the -1, that'd be 1/3. If it was a 4 to the -1, it'd be 1/4. And those fractions keep getting smaller and smaller and smaller. But is there anything that we could raise to the negative power, a negative power that would come out to 0? There's not. The fractions are just going to keep getting smaller and smaller and smaller over here, and closer and closer and closer to 0, but it's never going to reach 0. So you'll notice on this parent graph up here, do you see how on top of the x-axis, see it's kind of a dashed line drawn there? That dashed line is an asymptote. We've talked about that term asymptote before. It's been a while, okay? But remember, an asymptote is a value that we approach but never reach. Okay, so I'm going to go over this in red so you can see that a little bit better. So there's this dashed line at 0, at y equals 0 in the parent function, that the graph approaches on the left end, but it never reaches it. It just keeps getting closer and closer and closer to 0 as we keep putting in more negative x values. Okay, the further negative the x goes, the closer to 0 the y goes. But it's never going to equal 0. So that means that my range is never going to go past this y values, range is y values. This graph is never going to go below 0, is it? It never reaches 0, so it definitely can't go below 0. So my range is dependent upon where that asymptote is. Okay, and all exponentials are going to have an asymptote. So the range is going to come from 0, because remember, range is low to high. So 0 is the lowest it goes, but it never reaches it, so it's a parenthesis. And then it goes up to infinity. So the lowest the graph goes is 0, and it goes up to infinity. What about the domain? How far left does this graph go? What does that arrow tell us? Yeah, it keeps going left forever. What about to the right? Keeps going. So my domain is negative infinity to positive infinity in interval notation. Or if you want to write that as all real numbers, you can use the all real number symbol. Okay, so my domain for all, this is all exponentials, will always have a domain of all real numbers. The range, however, will be reliant on whatever the asymptote is. In the parent function, that asymptote is at y equals 0. Okay, because as those values, those x values keep getting more and more negative, we said those fractions will just keep getting smaller and smaller and smaller and closer to 0. Okay, but if that value, that base value is a fraction already, if that number is a smaller than 1 value, and we keep going left, 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 it reverses, because to get rid of the negative power, you have to flip it. So those numbers actually go up to the left when that value is less than 1. Okay, so that's how the graph changes from an increasing to a decreasing graph if you change the b value from greater than 1 to less than 1. It's because of that negative exponent rule. Okay. The same thing happens, though, as we go to the right in this one. The values will keep getting smaller and smaller and smaller and closer to 0, but never reach it. Okay, so, oh, I want red here. So both of these still have that asymptote at 0. It's just the different side of the y-intercept that approaches it. Okay, so here my domain and range are the same in both of these. 0 to infinity for the range, all real numbers for the domain. Okay, so it changed the behavior of the graph as far as increasing, decreasing, but it didn't change the domain or range. Both of these are still above that asymptote. We feel okay about that? All right, now, when we are graphing, we're going to be asked to graph the asymptote and graph at least 2 points. So the point that I would plot first would definitely be the y-intercept. And then you would graph a second point. And we usually want that point to be at an integer value, not a decimal. Okay, so oftentimes that second point will just be like when x is 1. Because like we set up here, anything to the 0 power is 1. And anything to the 1 power is itself. Okay, so that's another easy one to calculate, is when that x is 1. So for this one, for instance, if I plugged in a 1, 2 to the 1 power is just 2. So you can see there's a point at 1, 2. Okay, now here, because it's a fraction, to the 1 power would still be 1/2. So 1, 1/2. Okay, you can see that's a second point here. Okay, so let's try this with some examples now. So in this one, what is my b value? What is my base? What is the exponent of x on? A 3. So a 3 here is my base. So my base is 3. Is that greater than 1 or less than 1? So that means that this graph should be increasing, right? So this is going to be an increasing graph. Means it's going to have this shape like this. I know the shape that it should be. Now, the asymptote is going to be moved from the original parent function because there's this extra piece that says plus 2. Remember in all of our other functions, when we added something on the outside, that was our k value, right? Plus k at the end. And that shifted our graph up or down. We're going to talk more about this tomorrow, but it's the same thing with exponentials. If you have a plus k or a minus k, it's going to shift the graph up or down. And the asymptote shifts with the function. So instead of having my asymptote at y equals 0, my asymptote is going to be at y equals 2. So I'm going to go ahead and sketch that dashed line here where y equals 2. Okay, this is a horizontal asymptote for exponential functions. It runs left to right. Okay, so now I know where that is. Now I want to plot at least 2 points to graph this, and then I'm going to give the domain and range. So my y-intercept should be pretty easy to plot because anything to the 0 power, remember, is 1. So that would be 1 plus 2, which is 3. So there should be a point. When I input a 0, I get an output of 3. So my y-intercept is here at 3. And you'll notice that is shifted up 2. We said our vertical shift is up 2 from the parent functions. The parent function crossed at 1, and this is shifted up 2. Okay, now we need a second point. You can choose whatever you want to find for your second point. I think a power of 1 is really easy usually. So on mine, if I plug in a 1 as my exponent for x, 3 to the 1 power is 3, plus 2 is 5. So input a 1, I should get an output of 5. So 1, 5, there should be a second point. Okay, and that's enough then for me to sketch my curve. Okay, I followed the asymptote guides that in behavior, and then it should come up through those points. So I just needed to know that this is an increasing graph. I know where my asymptote is, and I've got a couple points. I can sketch this graph. So what would the domain here be? Bless you. Yeah, what I set up there is that the domain will always, for exponential functions, always all real numbers, going left and right forever. Now the range, we said, is dependent on that asymptote, okay? The range is going, the asymptote is going to stop the graph from crossing vertically, okay? So in this case, what would my range be? What's the lowest this graph's going to go? The 2 is the lowest. That asymptote's at 2. Now the graph is still going to go up to infinity. And remember, we don't include the 2 or the infinity. We cannot include an asymptote or infinity. So it's parentheses on both. Now, we are able to do this by hand, but what do you have access to? All right, let's check it. Let's use Desmos and check and see. Now here, I have just put in the parent function with a and b, because I want you to see this is where it starts, that y-intercept at 0, 1 that we talked about. Okay, I've got b set to 2 and my coefficient a set to 1 for the parent function. Okay, but if I change this, okay, that's the parent function. I'm going to put it is black. Now let's put what we have now. It's 3 to the power of x, and then on the outs, that was not a power. To the power of x. And then there was a plus 2. So here's the transformed graph. The graph shifted up 2, so our asymptote is here at 2. Our intercept shifted up 2, so it's up here at 3. And now the rate of change is slightly different because it's a base 3 instead of a base 2 like I had there in that one. You can see if I change this black one to a base 3, it got a little steeper. It matches a little bit closer. Okay. So you can see, you can play with this. Look at what that B value does to the graph. Okay. The smaller it is, the flatter, the longer it takes to increase. The higher it is, the faster it's increasing, the steeper it gets. Okay. And then notice when I get to 1, I said it can't be 1 because that would just be a flat line. Okay. But then when it is below 1, that's when it flips to decreasing. So you can play around and see how that B value affects your graph. Okay, but here's the one, and we can check those points that we said. We said there'd be a point at 1, 5, and there is. Okay, so that all checks out. So you can use Desmos to check your work, okay, and play around with those values so you can have a good visual of what they do to the graph. Now this one, what's our B value? The base value here that's raised to the power is 1/2. Is that greater than 1 or less than 1? So that means this graph should be decreasing. Do y'all agree? So it's going to be this shape this time. It's going to come down left to right. Now my K value, what's added on the outside, that's what affects my asymptote, is 1. So my asymptote is going to be at 1 instead of 0. So I'm going to go ahead and draw my asymptote at 1. Okay, now this time what's different is now there's something in the exponent with the x. There's that -3. That's our h. Okay, remember h is added or subtracted to the x on the inside of the function, and k is added or subtracted on the outside. Okay, so we have an h value this time. We'll talk more about it tomorrow in detail. Okay, but that's going to also affect our graph. Okay, but if I were to do the same thing, I've got my asymptote drawn. I just want to pick some values. If I were to plug in a 0 this time, it's not going to make this 1 because there's that extra +3 up there. So I'm going to end up with 1/2 to the -3 power plus 1. Okay, so it gets a little more complicated. So remember, I'm going to have to 2 to the -3. 2 to the 3 is 8, but to get it to a +3, I've got to flip it. So instead of being 1/8, this is going to become 8. And then 8 plus 1 is 9. And you can let the calculator do that for you if you can't do it by hand. But that's, if I input a 0 for x here, I get an output of 9. So that means my y-intercept is at 0, 9. Okay, now to get a second point, in the last one I input a 1, but because of that -3, I think it's easier to input a 3 here. Because what is 3 minus 3? So I think it's going to be easier to make that exponent 0. So if I input a 3 here, that's going to be a power of 0, and anything to the power of 0 is 1, and then plus 1 would be 2. So if I input a 3, I get an output of 2. So a point at 3, 2. So then I'm able to sketch this curve. And we already said it was decreasing. We knew that because the B value was less than 1. Okay, what's the domain here? How far left to right does this graph go? All reals. All exponentials will have the domain of all real numbers. Okay, what's the range this time? Still goes up to infinity, right? Goes up forever. But what's the lowest? Where's the asymptote? At 1. So it's 1 to infinity for the range. Now I can check that in Desmos. I can say, okay, let's see. Did I do that right? So this was the base. If I think it's a good idea to put your base in parentheses. So the base was 1/2. Now, if there's anything in your exponent with x, you are going to have to put parentheses to get it to be up there in the exponent. Otherwise, it'll keep typing the -3 down here. Okay, and then it was +1. Is that the right equation? Okay, so now we can see it. If you want to turn off the parent function, you don't have to look at it at the same time. Okay, so here, let's double check. Did that have a y-intercept? We said it would be at 9. That's correct. We did that. And then we said there would be a point at 3, 2. There sure is. Now, you could have picked a different point to plot. Okay, there's a point, it looks like at 1, 5. Okay, but we did this one. Okay, you only had to plot 2 points. Those are the 2 that we plotted. Okay, so that checks out. All right, last but not least, it gets a little trickier. What's different in this one? What does this one have that the others didn't? Yeah, that a value in front. Okay, bless you. That a value in front changes things. Okay, so the a value is an extra thing here we haven't seen yet. Okay, so what is my b value? What is being raised to the power? 3. And is that greater than 1? Okay, so we think that it should be increasing left to right, like this shape, don't we? But that a value comes into play, and this a value is negative. What is multiplying by a negative a do to our graph? So we're going to have to flip it. So if that flips upside down, it's going to look like this, isn't it? So that's what our graph should look like this time. It's going to be decreasing, but it's not going to look like this decreasing from left to right. It's going to be upside down. It's going to be under the asymptote, if you will. The asymptote is normally under the graph, but this flips upside down, so it's going to look like this. So that's how the negative is going to affect the shape of this graph. Now, where is that asymptote going to be? What's that k value? So the asymptote is going to be at y equals -4. So I'm going to go ahead and draw that. Now you could find this on by hand, like we did the others, plug numbers in and calculate to see where the points are. But you can also just use Desmos. I'm going to go ahead and go plug this into Desmos. So it's -2 out front. The base is 3. And it was x. What was it? Was there anything in the power with the x? +1. So here's the graph. Okay, so we can see, yeah, the asymptote's here at -4. That looks good. It looks like our y-intercept should be at -10. Okay, and then we need to get an additional point. All right, y'all will have some time to practice. Maybe use your cat tracks if you can. Try some of these in the Delta math. I'm going to finish this video here. All right, so this next point that I could plot, because I want it to be on an integer. I don't see one over here. Actually, yeah, right there should be one. Tracing, there it goes. -1, -6. So I'm going to plot -1, -6, and then the -10. So I plot a point at -1, -6. And then the y-intercept at -10. So those are the 2 points that I plot. That one wasn't supposed to change colors. Go. Okay, now I can sketch the curve through those. I use the asymptote as a guide, and then I know that it's coming down through those points. So what's different here, domain, still all real numbers. Come back up here, let me zoom out a little bit. But the range is going to be different this time because this graph is flipped under the asymptote. Instead of going from the asymptote up to infinity, this graph is going down to negative infinity. So it's coming up from negative infinity, because remember we always go least to greatest, and it's coming up to the asymptote, which is at -4. So the range had to flip because of that negative a value. Okay, so just be careful with that. And like I said, you can confirm that in your Desmos, okay, and see that we graphed it correctly. So you've got this practice in Delta Math here, and it's shortened, it's just 6 problems. So you're just going through and practicing graphing these exponentials. You can try to do it by hand and check with Desmos. You can just use Desmos for today while you get the hang of it. But we're going to go into more details on the transformation rules tomorrow.